Hello, today we're going to be talking about trusses, and we're going to be talking about how to compute the axial forces in each member. So if we're looking at this truss, we have all these different members, which would be from A to B, B to D, B to C, C to E, and we're taking all of these as single members. So they will all be connected somewhere here, which we would call a pin connection, there, 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 and so forth. So before we get going on that though, let's just talk about tension and compression. So if I have the two members and I yanked on it, pulled on it, if you grab the two ends of your pencil and pulled, that would be in tension. And if you got your pencil, just be careful with the lead, and you pushed in on it, that would be compression. So each one of these members we're going to have to compute whether they're in tension and compression, and we're also going to have to compute the force that's internally, the axial force in these members due to the forces that are acting on the truss. Now if I had a force acting over here or up over here or over here, somewhere else, the axial forces change. So this is just, the axial forces that we're computing is just based on the two forces on this beam that are acting on it. So our method for computing the axial forces, and this is the joint method, the first thing you would do is to look at the whole frame or the whole truss, and you would want to compute the reaction forces. And there are times that you don't have to do this, but there are times that you're going to have to do this. In this case, we're going to compute the reaction forces. Compute reaction forces, and that's using the whole frame. Okay, the whole frame. I'm sorry, the whole truss. Jeez. Alright, free body diagram. I guess you draw the free body diagram before you compute the reaction forces. And then what we're going to do is we're going to draw, and in this case I'd probably start here at joint A, draw each joint and the forces acting on it, and we're going to go through this example here in just a second. And then the last thing we're going to do is we're going to use our equilibrium equations to compute. Now typically this is just going to be my forces in the y and the forces in the x when I'm using the joint method. So let's go ahead and do this example, and what we're going to say here is compute. We're going to compute the axial force in each member and state if in tension or compression. So again, the first thing I would do is I would compute its reaction forces. So just to save time here, I'm going to go ahead and draw my reaction forces here, and I'm going to draw this one up here, and my force going up here. I'll call this GY, I'll call this AY, and I'll call this AX. Now if you look at this, we know that AX is going to be 0 because there aren't any other forces acting in the X direction. And then if I sum my moment about point A, and why would I do it about point A and not point G? Well, if I do it in G, I'd have two unknowns, or if I did have an X component, I should say. So in this case I could do it at A or G, but if there was some force acting over here, let's say, then you'd probably want to sum your moment here just to get the GY. So I sum my moment about point A is equal to 0. So I start here. As I move left to right, I have this 3 kilonewton force. And I know that it's going to be 1 meter away. As I moved again, 6 kilonewtons. So that's going to be, and yes, that was negative. And I have the 6 kilonewton force times 2 meters, which is also negative because they're both rotating clockwise about point A. And then I've got gy, so I've got plus gy, that's the force, and I've got to multiply by its distance, which is going to be 3 meters. It's all equal to 0. So plugging that into my calculator, I got 5 kilonewtons. Well, then I could sum my forces in the y, and if I sum my force in the y direction, I would have ay minus 3 kilonewtons minus 6 kilonewtons plus 5 kilonewtons. It's all equal to 0. So ay then would equal 4 kilonewtons. Now, everything that we have done so far is nothing different than we've done in class before. All we've done now, or all we're going to do now, is we're going to be computing the axial forces. But we're using equilibrium equations, and we're drawing free body diagrams. So the real new thing is computing the axial forces in each member. So I would start off by drawing joint D. Let's fix my pen there. And if I'm going to do this, I label it joint A. And I'm going to draw everything on there that I have. So that's going to be AB. And I'm going to draw this down. This is going to be AC. And I know I have this force going up, which we calculated to be 4 kilonewtons. And we have this force, but we knew that was 0. Now, if you think about it, I just kind of cut it right here. I'm just cutting it right there, and I'm looking at this force and this force. And we know that this force is acting this way and acting this way. Now, the way I drew this are in tension. So I draw the free body diagrams, or the forces in the free body diagrams, draw the forces in the free body diagrams in tension. Meaning it's pulling on this joint, right there. It's pulling on it, so it's keeping this in tension. Now, if my answer comes out negative, then I would know that it's in compression and it's actually pushing back into this point. So if you look at this joint, if I sum my forces in the x, I'd have 2 unknowns. If I sum my forces in the y, I only have 1 unknown. Now I know that this is 45 degrees, or I like to use 1 square root of 2, which is the same thing. And I'm going to sum my force in the y direction. That's equal to 0. So I have 4 kilonewtons, which is in the positive direction, minus the axial force AC times 1 square root of 2 is all equal to 0. Now, using those cool algebra skills, I can say that AC is going to equal 5.65 kilonewtons. Now, when I moved this over, it became positive. So my answer comes out positive. It's in tension. So I know that this right here is in tension. If I sum my force in the x direction now, I have AC, which I know is 5.65 kilonewtons, times 1 square root of 2, 1 over the square root of 2, plus AB. Now when I take this over, it's going to become negative. So AB is actually going to be 4 kilonewtons, but it comes out negative, so this is actually in compression. That's in compression. Alright, so let's look at the next joint. And since I've solved for this one, I solved for this one, I went ahead and looked at joint C. Because I have this force, and I can find this force and this force. Also, I have to include this 3 kilonewton force because I'm looking at this joint. So if I'm looking at joint C, I would draw it out. And I've got one going up, and I've got one going here, and I've got my 3 kilonewton force. Now let's talk about this real quick. We said that AC computed to be 5.65 kilonewtons in tension. Now I drew that in tension. So remember, it's being pulled away from point C, so that's going to be in tension, and that's 5.65 kilonewtons. We need to solve for BC, and we need to solve for CE. So if I sum my forces, again, if I sum my forces in the y direction, I have one unknown. If I sum my forces in the x direction, I have one unknown. So let's just go ahead and sum my forces in the y direction. When I sum my forces, I'm going to have 1 over the square root of 2 times AC, which was 5.65 kilonewtons. And I have, let's see, plus BC, that's my unknown, minus 3 kilonewtons. That's going to all equal to 0. So computing this, BC should equal negative 1 kilonewtons. So it is in compression. If I sum my forces in the x direction, same thing. Now this component is going in a negative direction. So if you think about this, x direction, x component of 5.65 is going negative, so I'm going to put negative 5.65 kilonewtons times 1 over the square root of 2 plus, because CE is going in the positive direction, plus CE is all equal to 0. So when I move this over to the other side and compute, I got that CE is equal to 4.0 kilonewtons in tension. So I'm just going to kind of come over here and scroll and mark the ones I've computed. So I've computed those, or I've computed AB, AC, I've computed BC, I have computed CE. So really, I need BE, BD, DE, DG, and EG. Phew, that's a lot to say. So what did I do next? Well, I did joint B. So I looked here at joint B. Joint B. And I'm going to go ahead and draw it out. And sometimes I like to do this. I like just to go and draw out my lines. And I've got one going down. And I've got one going here. Now, a lot of people will say, well, what about this 3 kilonewton force? Can't disagree with what you're thinking, but remember, I'm just cutting those. If I cut this out and I erase everything else, all I'm looking at is what's happening at joint B. So I've had force BD, force AB, force BC, and force BE. That's all I'm looking at. So we calculated earlier AB was negative 4.0 kilonewtons. So if I'm going to draw this correctly, it's actually going into the joint. It's compressing into that joint. If we're looking at BD, we're solving for that. So I draw it in tension. BE, I'm also drawing in tension because I'm also solving for BE. But BC we have computed, and we said that was also negative 1. So that's also going to be compressing into joint B. So it's going to be going up. So this is 1 kilonewton. And this was, AB was 4 kilonewtons. So it's just the direction that we're looking at, whether it's compressing or it's in tension. So it's, again, 4. We got 4 up here was negative 4. So it's compressing into joint B. 1 kilonewton we calculated was, member BC, negative 1. So this is being compressed. So you can think of it like it's being pushed in to BC. So we have everything labeled and everything we need. So I'm going to sum my forces in the y direction. Is equal to 0. So I have 1 kilonewton. Remember, because now it's going up, I'm showing that this is going up. And this is negative BE times 1 square root of 2 is all equal to 0. So BE comes out to be a positive 1.41 kilonewtons, and that's going to be in tension. Sum my forces in the x direction, and that's going to be 4 kilonewtons. That's going to be positive. I've got plus, now I've got to look at BE. I just solved for that. That stayed in tension, so it's still going out. So its x component is still positive. So I'm going to go ahead and write that in 1.41 kilonewtons times 1 square root of 2. And I've got the last one is plus BD. So all equal to 0 because I have BD. So computing for BD, it came out to be 5 kilonewtons. But yep, you're right, it's negative. So that's going to be in compression. Alright, so now, if I get my little green marker again, I have solved for this one and this one. So really all I have is 1, 2, 3 left. 3 left. So I'm going to do, I can squeeze this one in right here. I'm going to do joint E. So joint E is right here. Again, I can cut this like this. Now I'm only looking at CE, EB, ED, and EG. So I'm going to go ahead and write what this looks like. Draw the free body diagram. So we know that this 6 kilonewton force is a given. We know we're solving for EG, so we put it in compression. We know we're solving for DE. We draw in tension. Now let's look at EB. When we go back and we look at EB or BE, we said it was 1.41 in tension. So again, we draw in tension 1.41. Sorry about that. Kilonewtons. And then let's look at CE. CE was also 4 in kilonewtons, and that's also in tension. So again, I draw going away from the joint because it's in tension. So if I sum my forces in the Y here, I'm going to have DE, which I'm solving for, DE, plus, now I've got this 1.41 kilonewtons, and its Y component is going up, times 1 square root of 2, and then I have this negative 6 kilonewtons here, because that is going down. That's this force right here. That's all going to equal 0, so DE is going to equal 5 kilonewtons in tension. And if I sum my forces in the X, and you can see this gets kind of tedious if you're having to solve for all the axial members in the truss. Pretty much what we'll be doing for homeworks and stuff is solving for certain members. So we can be solving for this one, and this one. But for practice, it's good to do all the members in the truss just to get some good practice. So if I sum my forces in the X, I have EG, which is going to be positive, minus 1.41 kilonewtons times 1 square root of 2. That's this one here, and you can see that it's going in the negative direction. The component for this one is going in the negative direction. Times 1 square root of 2. And then I have this 4 kilonewton is also going in the negative direction. Now I know I said that this is positive. We came out that this was positive in tension, so we drew it in tension away from the joint. But now when we do equilibrium equations, just realize that we're just looking at direction of that force vector. So EG comes out to be 5 kilonewtons as well, and that's also in tension. So now we have solved for DE and we have solved for EG. So the last one we have to do is this member right here. Now I could do joint D or I could do joint G, which I'm going to choose. Let's do joint G. Joint G. I'm going to draw it out. We computed Gy up here as 5 kilonewtons. And I know I'm solving for dg, so that's going to be put in tension. Now really, I don't even need to look at Eg, although I could say that was in tension at 5 kilonewtons. And I know this is 1 square root of 2, and we're solving for dg. Now I could sum my forces in the x, or I could sum my forces in the y, and you could tell that you're going to get the same answer either way, because both of them are 5 kilonewtons, and this is a 45-degree angle. So if I sum my forces in the y direction, I'm going to get that dg times 1 square root of 2, that's going to be positive, plus 5 kilonewtons is equal to 0. So we come out that dg is equal to 7.1 kilonewtons, and that's going to be in compression, because if you look at both of these are positive, you take one to the other side, that should become negative. Now if you did the same thing in the x component, you'd have a negative 5 kilonewtons, and then a negative dg 1 square root of 2, so you'd also get a negative 7.1 kilonewtons. So again, this is the joint method, and if we kind of went back and looked at our method again is draw the free body diagram, then compute all the reaction forces using the whole truss now, using the whole truss, showing all the external forces on the truss, which was the two forces acting down, which was 3 kilonewtons and 6 kilonewtons. And then you're going to draw the free body diagram of each joint, and then you can use equilibrium equations to solve. Sometimes you can look at a truss and it'd be easier to start at this joint, or it would be easier to start at this joint. If you have like 6 or 4 members or 5 members coming off of one joint, and you only have one known, you probably want to start at another joint in order to solve for some of the other members to help you compute the rest of them. So I hope this helps a little. I am going to upload another example for the joint method, and then I'm also going to upload a few of the sections, method of sections. And that's how you do trusses, axial forces. And what's the reason for doing this? Well, a member that's in tension. So if we kind of looked at this really quick, and we looked at AC, we said this was in tension, right? And then we looked at AB, and this one was in compression. So this beam, or this member is in compression, and this member is in tension. Well, we might not use the same size of steel or whatever we're using, because one might be better in tension and one might be better in compression. So maybe a thicker steel, maybe a lighter steel. So those are the things that you'll be looking at in your materials class. But right now we're just solving for the axial loads acting on the member depending on our external forces on the truss. Remember, I could put other forces on this truss, and it would change all of these answers depending on our external loads. Alright, thanks for listening.